Okay, so welcome back. In the last video, we showed that you can calculate the number of electrons on the N side to the number of electrons on the P side of a p-n junction, and found that it's related to the barrier height. In other words, it's related, if you remember, the barrier height's dependent on the material parameters, but also importantly on the doping that you introduce to the junction. And so it's not a surprise, perhaps, that the number of carriers that are generated in both the N side and the P side are related to this barrier height. And equation 25 is the expression for this. You are then going to, and I hopefully have now, done the same thing for holes by integrating the variation of hole concentration as you move from the P side to the N side. In the P side, the maximum concentration of holes is number of carrier concentration of holes is P subscript P on the P side, and P subscript N as you move into the N side, as you move from the region X1 to the region X2. And then you have the same barrier height, VBI, phi B, and you get this expression here in equation 26. You can see that the right-hand side of the equation, the exponentially dependent term on the barrier height is the same for both electrons and holes. The ratios are the same for the electrons and holes. And so you can combine these results to give you equation 27, which is this, or more commonly, you can just change the way that that's written, show it's really the mass action law again, to show that the number of carriers in the N side, on the left-hand side here, is the same as the total number of carriers on the P side, on the right-hand side here. These subscripts are N, so it's showing you that the total number of electrons multiplied by the total number of holes is equal to a constant, which is equal to the number of carriers, number of electrons on the P side, NP, times the number of holes on the P side, PP. But all of these are for an unbiased junction. This is the situation in equilibrium, which is why we've got these subscript zeros, because no voltage has been applied. But in fact, when we apply a voltage, we need to add that on to the barrier because it changes the barrier height. And so we do that, we can then get to equations 28A and 28B. A is for electrons and B is for holes. You can see, if we just look at the case for electrons here, this is electrons in 28A, that what we're showing is that if you have a positive voltage, VA, which is applied, in other words, you're in forward bias, then the ratio NN over NP here is going to decrease, and that is showing you that the minority carrier concentration here, NP, N subscript P, is increasing. So you are getting a higher number of minority carriers when you apply a positive bias. Okay, in forward bias. So forward bias increases the minority carrier concentration. If you apply a negative bias, so VA is negative, which is a reverse bias, then this ratio is going to increase. In other words, the number of minority carriers, N subscript P, is going to decrease. Okay, so you are having fewer minority carriers, in this case electrons, by introducing a reverse bias. And you can see why that works. The same thing occurs in equation 28. It's just showing you the same thing for the holes. So it's the relationship PP over PN. And you're showing that you can vary, or that you do vary, the number of minority carrier concentrations of both electrons and holes when either a forward or reverse bias is applied. In the case of a forward bias, you're increasing the minority carrier concentration, whereas in the case of a reverse bias, you are decreasing the minority carrier concentration. Okay, so the important thing here is that you are also changing the majority carrier concentration, the top part of these equations, 28 and 29, but actually the change is very small, because remember, when you're in the sort of N-type region, there's already so many electrons because of the doping that even though you would be changing the carrier concentrations in this region as well, it's pretty insignificant compared with the majority carrier concentration that's already there, the number of electrons that's already there. So we tend to say that we approximate that the majority carrier concentration, which is either NN or PP, is going to remain constant at its equilibrium value. And if you remember, the equilibrium values is N0 and P0. So yes, NN will change and PP will change when you apply a bias, both forward and reverse, but actually we're going to assume that they remain constant because it makes the, and it's fair to do that because of the large numbers involved. So we then divide by the expressions 25 and 26, okay, because we know we need to get rid of these, we want to get rid of and simplify the equations in 28, in equations 28 and 20, sorry, 28A and 20B. And when we do that, we get down to equations, so you'll have to turn over the page, I believe, and you get down to equations 31A and 31B, which is on the next page and in a square. So these are very important equations here, and the reason they're important is hopefully for the reasons I've just said here, is that they're showing that when a forward bias is applied, when VA is positive, the minority carrier concentration close to the junction is going to increase, okay? And when a reverse bias is applied, the minority carrier concentration will decrease. So just making sure you understand what this term is, NP is the minority carrier concentration when a bias is applied, NP0 below is the minority carrier concentration at equilibrium when the bias is not applied. So the relationship between NP over NP0 is just showing you the ratio. So you can tell if the ratio is going to increase or decrease, and it will actually increase. The minority carrier concentration will go up when there's a positive forward bias, and it's going to decrease when there's negative forward bias, a negative bias, in other words, a reverse bias applied. So we can look at that on a picture. These are not band diagrams, I have to make clear. These are simply showing you how the carrier concentrations, and in particular the minority carrier concentrations, will change, as we've just been discussing with equations, but sometimes it will help you to look through at the pictures as well. So in the case of a reverse bias, when we apply a negative voltage to the P-type region, that would be a reverse bias here. You can see that from the battery going through. You've got the P-type region, the N-type region, the depletion region in the middle, and you can see that the reverse bias is, this is the carrier concentration, okay? It's going downwards from its equilibrium value. So NP0 is the equilibrium value of the minority carrier concentration. When you've applied a reverse bias, it's going down from its equilibrium value to its new value, N subscript P. That's on the P side. The electrons in the P side are the minority carriers on the P side. If you look at now at the N side, the minority carriers are holes, so that's why we've got P's. And at equilibrium, if there was no bias applied, the level would be up here, so it would be P subscript N at naught, P subscript N naught, equilibrium value of holes on the N-type side. However, when a reverse bias is applied, you are reducing the concentration of minority carriers, especially at the junction. And then you've got a gradient as it goes back to its equilibrium value further away from the junction. So that's the case for the reverse bias. If you now move over to look at what happens under a forward bias, you can see a positive voltage is applied to the P-type side. The equilibrium values of minority carriers are the same in both the P side and the N side. And this dotted line here, on the P side, the minority carrier concentration is N subscript P, it's the number of electrons in the P side, whereas in the N side, it's the number of holes in the n side, so we call that P subscript n, and the 0 is for equilibrium. But when we apply a forward bias, we are increasing the number at the junction, okay? So that's why it's gone up, and we now call it n subscript P. There's no 0 because a bias is applied. Same for the n side, we now call it P subscript n. So you can see that you've got a big variation in the number of, or rather the concentration of the minority carriers, both with a reverse bias and a forward bias. Okay, I hope as well that you're going to be able to see, we haven't got there yet, but because you've now increased it at the depletion edge, it's no longer constant through the semiconductor. And if it's no longer constant, it means there's a variation which can give rise to a diffusion current. And that's why it's so important to understand the operation and understand how the diffusion current works, because you can see that in any PN junction, by applying a bias, you're generating a gradient. The gradient was going to give rise to a current flow, a diffusion current flow that wouldn't otherwise be there. And it's by having this gradient, which is why you actually get current to flow across a PN junction, dependent on the bias. And this is how the devices, all devices, really operate. So the PN junction has a depletion region, which is wider. You'll need to work down when you're in reverse bias. You've got a larger potential applied, and you're increasing the size of the depletion region. If you come up to here, you will see that these diagrams are really simply going through the maths before it, but it's much easier to see on a diagram, I think, than just by following equations through. But try to make sure that you understand how they work together, and also why this gradient that's been introduced is so important, and how the gradients are relating. I'll just go back and show you to these equations here, 31A and 31B. The gradients is the relationship between the minority carriers with a bias applied, say Pn, compared with its equilibrium value, Pn0, or for the electrons Np over Np0. But it's this ratio, that's how much the gradient is going to increase by. Pn over Pn0, say, is exactly what we're looking at on this diagram here. It's the Pn, how much you've increased the minority carrier concentration relative to its equilibrium position. That's going to tell you what your gradient is, and therefore it's going to tell you what is the effect on the current density when you come to calculate it. And that's the part that we will do next. So you can see that the gradient is important, okay? The increase in carrier concentration, or rather minority carrier concentration with voltage applied. I've already said that the majority carrier concentration will also change. If the minority carrier concentration changes, then it's inevitable that the majority carrier concentration will change. But this is a very small amount relative to the minority carriers, and so we're going to ignore that change and focus on calculating what is the difference in the minority carrier concentrations. So we have an example to demonstrate what the values or the changes could be in these minority carrier concentration. And the question is, if we assume a silicon PN junction, we need to know the doping level, and we're given that here. The P-type doping comes about from the acceptor doping concentration, and that's given here. The Na is the acceptor doping concentration, is 1 × 10⁻17 per cubic centimeters, and the N-type doping comes about from donor doping, so in other words, group 5 doping. So the donor concentration, N subscript D, is 1 × 10⁻16 per cubic centimeters. So we call that Na and Nd. And then we're being asked to calculate the changes in the minority carrier concentrations. Those are Np and Pn when a forward bias of 0.3 volts is applied. Okay. So the first thing we have to remember, I've already written it and given you a big help because people often get confused. You've got Na and Nd. So you need to remember that that Na gives the acceptor doping. Accepted doping is what gives you the p-type doping. And p-type doping means the majority carrier concentration, okay, in the p-type region. So really, instead of writing P, we should write that is the p-type, the number of holes in the p-type region. So we tell you that by writing a subscript P. Same for the donor doping, it's the number of, or the concentration of electrons in the n-type region. So now we have to be clear that we're really referring to Nn, N subscript N, and that helps clarify things. We're going to assume that there's full ionization of the dopant, because if you remember, I said that sometimes your acceptor doping may not generate an equal number of holes or an equal number of electrons, but we're going to assume that each of these atoms does give rise to an extra electron, and each of these acceptor atoms is going to give rise to one extra hole. So that's called full ionization. And then, as I've just written, you can assume that your p-type doping is 10 to the, or the number of holes is 10 to the 17, and your n-type doping is 10 to the 16. If that's the majority carrier concentration, it also means that we can work out what the minority carrier concentration is at equilibrium. And because we're at equilibrium, we can also say, we've said before, that actually it doesn't make a difference, but we'll put the 0 in there just to keep clear. We know that in silicon, the intrinsic carrier concentration is around 10 to the 10 per cubic centimetres. We know that the number of electrons multiplied by the number of holes in either the N or the p-type side is going to be equal to a constant, which is related to the Ni squared. So we know that Ni squared is around 10 to the 20. So that means in the p-type region, we have to have an electron concentration at equilibrium of 10 to the 3. Okay, so we have number of electrons in the p-type region times the number of holes in the p-type region has to be 10 to the 20 per cubic centimetres. We know that pp is 10 to the 17, okay, that's 10 to the 17, it's given in the question, it's coming from here. So this number of electrons, np, or np0, is equal to 10 to the 3. Okay. We then go back to our equation, equation 31A, because 31A is the equation that relates the carrier concentration to the voltage applied. So this is equation 31A. This is our expression. We have NP over NP0. That's what we're trying to find out. And we have already worked out what NP0 is. It's 10 to the 3. Okay. So if I just show you here, NP0 is 10 to the 3. This is equation 31A. And the equation is simply showing that NP is equal to NP0 e to the Q over KBT times VA. Okay, and that, I hope you can read this, is what this equation here is showing. It's 10 to the 3, that comes because we know that that is NP0. We've calculated that, and NP was Ni squared. 38.65 is simply Q over KBT. That's a constant in your data sheet. And this 0.3 is your applied voltage. So that gives us an equation. This is where it's from. This is equation 31. That gives us an equation or a value of NP, which is equal to 1.09 times 10 to the 8 electrons per cubic centimetre in the p-type region. Okay. We now do exactly the same thing for holes. Here we know that in the n-type region, there must be 10 to the 4 holes at equilibrium, and that is because in the n-type region, the number of electrons is equal to 10 to the 16, and we know that n times p is equal to 10 to the 20. Okay, So therefore, we can calculate, or we don't even need to calculate it, we can figure out that Pn naught must be 10 to the 4. So we're now going to use equation 31b, which is exactly the same. This is equation 31b, and put 4 into our expression, okay, because we know that that's what Pn naught is. So Pn naught is 10 to the 4. 38.65 is still Q over kBt, the constant, and the number and the voltage applied is 0.3 volts. So if we obviously use our calculator for that, we're going to see that the number of holes in the n-type region with 0.3 volts applied is 1.09 times 10 to the 9. So if we compare these values, because remember, we're really looking at the comparison of the equilibrium values and the new values with the voltages applied. So it's the ratio Pn over Pn naught, Pn naught, and N in P over N P naught. We're looking at the ratios. We can see that both of them have increased compared with their equilibrium values of around 10 to the 5. Okay, and we get that by looking at equations 31 and 32. So we started out with 10 to the 3, and we started out with 10 to the 4, and we've now, the 10 to the 3 one has gone up to 10 to the 8, and the 10 to the 4 has gone up to 10 to the 9. Okay, so that's the number of holes has increased by a factor of 5 orders of magnitude, and the electrons here has also gone up from 10 to the 3 times to 10 to the 8. So in both cases, there's an increase of 10 to the 5. So that is a really quite a significant increase, and much bigger increase than you would see for the majority carrier changes, which is why we neglect it. In the next section, we're going to go on to use these values in order to calculate the current flow, because we've already shown there's a diffusion gradient.